Okay, welcome back everybody. This is the worked examples section for orthonormal bases, Gram-Schmidt method, and vector representations revisited. Let's just start out that I am going to use the acronym ONB for the rest of this semester. I'm definitely not the only one in mathematics. I would say a vast majority of mathematicians use the acronym ONB to mean orthonormal basis. So if you ever see me saying ONB instead, I'm going to work with that. Let's also just remember this object, delta ij, as the Kronecker delta, satisfies that it's equal to 1 when I is equal to j, and 0 when I is not equal to j. As an example, delta 1, 1 equals 1, delta 1, 2 equals 0, delta 1, 3 equals 0, delta 3, 1 equals 0, delta 3, 3 equals 1, delta 2, 2 equals 1, delta 2, 3 equals 0. Have your pick as to how many of those you want to do. Just compare the top versus the bottom. If they're different, you get a 0. If they're the same, you get a 1. Anyway, we're really only going to work through one example today, but it is quite the lengthy one. And we're going to get good at all three of the topics in our one example. So let's just start out with our one example, and you'll see what it is and figure out why we're going to be good at our three topics. Consider the set of vectors 1 plus I, 1 minus I, 0, 1 minus I, 1 plus I, 0, and 1, I, 1. This set of vectors is a subset of the three-dimensional complex numbers. We're going to do three things to this. So first, execute the Gram-Schmidt method on this set. Secondly, verify the output of the Gram-Schmidt method is an orthonormal basis. And thirdly, compute the vector representation or basis decomposition, I should say, basis decomposition of the vector 2, 1, 0 with respect to the ONB created. So we're going to create an ONB in step 1. It'll have some form E hat 1, E hat 2, E hat 3. Step 2, we're going to verify with Gram-Schmidt that this is an orthonormal basis. I could call this E hat sub I, by the way, I in the set 1, 2, 3. In step 2, I would verify that E hat sub I, E hat sub j equals the Kronecker delta, ij, which is equivalently 1 when I equals j, and 0 when I is not equal to j. And then in step 3, this 2, 1, 0, we're going to allow it to be 2, 1, 0. We're going to write it in the form C1, C2, C3 for some collection of constants with respect to the basis that we create. And keep in mind, that's equivalent to saying it's C1 times the first vector plus C2 times the second vector plus C3 times the third vector. And because it's an orthonormal basis, we can get away with noticing that C sub I equals the inner product of our original vector 2, 1, 0 against E hat sub I. That's going to be our job for today. Let's try the first step, which is the Gram-Schmidt method. So for that, I'm going to go ahead and give these names V1, V2, V3. And using my Gram-Schmidt method, our first step, we can recover E hat 1 by normalizing v1. In this case, v1 was the vector 1 plus I, 1 minus I, 0. We can normalize it by computing the magnitude squared of 1 plus I, the magnitude squared of 1 minus I, and the magnitude squared of 0. If I take the magnitude squared of a complex number, as always, I'm looking at the two coefficients, in this case 1 and 1, and I'm going to square them and add them together. Same in the second case, my coefficients are 1 and negative 1. I'm going to square them and add them together. And in the third case, my coefficient is just 0. Looks like I have 4 copies of 1 there, so that'll be a square root of 4 in the denominator, also known as 1/2. If I wanted to, I could distribute the 1/2 to the inside, but I won't. I think actually a lot of times with Gram-Schmidt and even other vectors, once I normalize them, it is actually to my advantage to just leave them out front. Anyway, I've found E1 now. To find E2 hat, I'm going to take V2, I'm going to subtract the inner product of V2 against E1 hat, and multiply that by E1 hat. I'll then have to normalize everything. If I just compute the numerator here, we can extract V2 all the way from up above. Here it is. So I can extract that as 1 minus I, 1 plus I. And 0 in the third component. I'm going to subtract the inner product of that, 1 minus I, 1 plus I, and 0 against what I've just computed, E hat 1, 1/2, 1 plus I, 1 minus I, 0. And then that also drops down to the side here, 1/2, 1 plus I, 1 minus I, and 0. At this stage, because it is an inner product, I can move the 1/2 as a scalar out front, and I'll have a 1/4 sig around if I want to. To that end, I'll go ahead and compute the rest of the inner product terms. The inner product terms here, if I'm looking horizontally, keep in mind, because it's complex valued, I need a conjugate on the second terms. And I'm multiplying across horizontally, and then I'm going to add those terms together. So multiplying across, I have 1 minus I, and then the conjugate of 1 plus I. And then I have 1 plus I, and the conjugate of 1 minus I. And finally, I have a 0 times a 0. If I want to simplify this further, I can. And I'll have 1 minus I times 1 minus I plus 1 plus I times 1 plus I. Those sign changes are happening due to the conjugate. And now I'm going to FOIL everything. So if I FOIL everything, I have the first gives me a 1, the outside gives me a minus I, the inside gives me a minus I, and the last two terms give me negative I squared. So positive I squared is negative 1, I have a minus 1. I'm then left with plus, the first gives me 1, the outside gives me I, the inside gives me I, and the last gives me a positive I squared, also known as minus 1. Looks like I have a 1, minus 1, those cancel. I have a 1, minus 1, those cancel. I have 2 negative i's and 2 positive i's, so those are also going to cancel, and I'm going to be left with 0. So my inner product term there turned out to be 0, making this entire piece turn into 0. So because that turned into 0, I'm able to just work with this as my numerator. Well, that's easy enough then. If I work with that as my numerator, I have 1 minus I, 1 plus I, and 0. I'm going to divide it. Keep in mind, this is just the magnitude of the numerator. And so all I have to do is divide by the magnitude of the numerator, which, because it's complex valued, I'll be looking at the magnitude of 1 minus I squared, the magnitude of 1 plus I squared, and the magnitude of 0 squared. As before, this is going to give me, looking at the coefficients, 1 and negative 1, 1 squared plus negative 1 squared, plus 1 and 1, 1 squared plus 1 squared, plus 0 squared. as before, I have 4 copies of 1, also known as 4. So it's going to be 1 divided by the square root of 4, also known as 1/2. So there is E hat 2. In step 3, E hat 3 is going to be produced from both of the previous E hats. It's going to be V3 minus the inner product of V3 against E hat 2 multiplied by E hat 2 minus the inner product of V3 against E hat 1 multiplied by E hat 1. Then going to divide by the magnitude of everything. To recover E hat 3. As before, I'm going to calculate the numerator all by itself first. And what is V3? We have to scroll all the way back up to see that V3 was 1i1. V3 is going to be 1i1. I'm going to subtract the inner product of V3 against E2, which I've just calculated, as 1/2, 1 minus I, 1 plus I, 0. And that multiplies E2, which I've just calculated, as 1/2, 1 minus I, 1 plus I, 0. I'm also going to be subtracting the inner product against E1. So V3 is over here as 1, I1 against 1/2, 1 plus I, this is going to be E1 now, 1 minus I and 0, multiplying 1/2, 1 plus I, 1 minus I, and 0. Going to have to go through some work to calculate these inner products, but as always, I can move the 1/2s out to just give me a 1/4. Let's go ahead and look at the inner product of these two terms. The inner product, I'm going to look horizontally, is going to be 1 times 1 minus I conjugate, you always gain conjugates, plus I times 1 plus I conjugate, plus 1 times 0. This will simplify to 1 plus I plus, now this 1 plus I that has a conjugate will be 1 minus I. If I'm multiplying that by I get an I, and then negative I squared, also known as 1. This ends up being 2 plus 2I. I can do a similar thing with this inner product, and notice that I have a 1 times 1 plus I conjugate, plus I times 1 minus I conjugate, plus 1 times 0. This will be equal to 1 minus I, plus I'll have an I times 1 plus I. So I will have an I here, and then 1 plus I times I is I squared. So that'll give me a minus 1. And we can see we have a minus I, and a plus I, a positive 1, and a negative 1. So I end up with 0 here. Okay, so we just found out that this entire term became 0, which means the only term that's contributing is this 2 plus 2i, which can replace that inner product. That means our numerator is going to be equal to 1i1 minus, there was still a 1/4 from both copies of 1/2, as well as the 2 plus 2i from the inner product itself. We can write that as 2 plus 2i over 4, or we can write this as 1 plus I divided by 2. That's going to multiply the very last term, 1 minus I, 1 plus I, and 0. At this stage, it is going to be to my advantage to distribute the 1 plus I over 2 to all three terms in there, and we'll end up with 1i1 minus 1 plus I times 1 minus I. Because these are conjugates of one another, they will produce the magnitude squared for me, which is always going to be equal to the coefficients squared added together. So that's going to be equal to 2 divided by 2, and I'll just get 1. In the second case, I'm going to have to FOIL. I'll have a 1 squared plus I minus 1 because of an I squared, and I'll end up with 2I. 2I divided by the 2 in the denominator is just going to give me I. And finally, in the third component, because I have a 0, I have a 0. This means that what I'm subtracting from 1i1 is 1i0, and I'm just left with 0, 0, 1. Now we'll notice that in fact 0, 0, 1 is already normalized. So that's quite exciting, and it means I don't have to worry about the entire denominator here because I already know that 0, 0, 1 is normalized. That means that E3 is the vector 0, 0, 1. So Gram-Schmidt then has given me my set E hat 1, E hat 2, E hat 3 as 1/2 times the first vector, 1/2 times the second vector, and the third vector has become 0, 0, 1. So this is 1/2, 1 plus I, 1 minus I, 0, 1/2, 1 minus I, 1 plus I, 0, and 0, 0, 1. The second thing I was asked to complete is to verify that the output of this method is in fact an orthonormal basis. So let's go ahead and do that. Let's verify that this set, 1/2, 1 plus I, 1 minus I, 0, 1/2, 1 minus I, 1 plus I, 0, and 0, 0, 1 is in fact an orthonormal basis. To do that, I need to compare all inner products of vectors with themselves, and I hope they are all 1. And I need to compute all inner products of vectors with each other and hope they are all 0. So let's do them with themselves first. So I'll grab this case and do it with itself. 1/2, 1 plus I, 1 minus I, 0, with 1/2, 1 plus I, 1 minus I, 0. I'm going to have both 1/2s come out as 1/2 squared, or 1/4. Then I'm going to be reading horizontally and computing a complex conjugate of the term on the right. This is going to give me 1 plus I times 1 minus I, the conjugate of 1 plus I. And then I'm going to get 1 minus I, 1 plus I, which is the conjugate of 1 minus I, and then I'll end up with 0 squared. If I FOIL these, I have 1 minus I plus I minus I squared is plus 1. Then I'll have plus 1 minus I plus I minus I squared is still plus 1, and then the 0. The i's and minus i's cancel. I have 4 copies of 1, so I have 4 divided by 4, and this is in fact equal to the 1 that I was hoping. I can do the same with the second vector here and compute 1/2, 1 minus I, 1 plus I, 0, against 1/2, 1 minus I, 1 plus I, and 0. And I'm going to read horizontally and take the complex conjugate of the terms on the right. As before, the 1/4 comes out, and I'm left with 1 minus I times 1 plus I, the conjugate of 1 minus I, and I'm left with 1 plus I, 1 minus I, the conjugate of 1 plus I, and a 0 squared. Foiling, just as before, I have 1 minus I plus I minus I squared is plus 1. I have 1 minus I plus I minus I squared is plus 1. And just as before, the minus i's cancel, and I have 4 copies of 1. 4 over 4, which equals 1. Verified. The last case, 0, 0, 1, is incredibly straightforward, but I'll write it out anyway. 0, 0, 1 against 0, 0, 1 is going to be read off horizontally as 0 times 0, 0 times 0, and 1 times 1, which does in fact equal 1. So I verified all inner products of vectors with themselves, that they're all equal to 1. Now I'll need to compute all inner products of vectors with each other, and there's going to be 1, 2, 3 possible cases of vectors with each other. That's because if I swap the order of the inner product, it doesn't matter if I do 2 or 3 first versus 3 or 2 first, because the complex conjugate of 0 is 0. So I'm going to be computing 1, 2, 3 different choices of these interactions. And we'll do 1 first, which is the inner product of the first 2 entries. This is going to look like the inner product of 1/2 times 1 plus I, 1 minus I, 0. Inner product with 1/2, 1 minus I, 1 plus I, and 0. The 1/2s come out front for free, and I'm going to read horizontally 1 plus I times 1 minus I conjugate, 1 minus I times 1 plus I conjugate, and 0 times 0. It's going to leave me with 1 plus I times the conjugate of 1 minus I, which is 1 plus I. I'll then have 1 minus I times the conjugate of 1 minus plus I, which is 1 minus I, and then I'll have 0 squared. If I FOIL my terms out, I end up with 1 plus I plus I plus I squared, which is negative 1. And then FOIL again, I have 1 minus I minus I minus minus I squared. So plus I squared is minus 1. In this situation, my 1's cancel, and 2 copies of I cancel with 2 copies of negative I. I'm left with a total of 0 over 4, which is 0. I can then check the second case, which is my first vector against my third. This will be the vector 1/2 times 1 plus I, 1 minus I, and 0 against the vector 0, 0, 1. If I multiply across horizontally, I have 1 minus I times 0, 1 minus I times 0, and 0 times 1, also known as 1/2 times 0 plus 0 plus 0, and I certainly have a 0. If I do the third case, that's going to be the second vector times the third vector, and I can compute that as 1/2, 1 minus I, 1 plus I, 0 against 0, 0, 1. This will give me a 1/2, reading off horizontally, 1 minus I times 0, 1 minus I times 0, and 0 times 1. Again, 3 copies of 0. So I end up with 0, and I'm verified. All 3 intertwined terms are equal to 0, and therefore I have verified that this is an orthonormal basis. Finally, my job for today is to compute the vector representation, or basis decomposition, it's the same thing, of the vector 2, 1, 0 with respect to the orthonormal basis I've created. So let's grab the vector 2, 1, 0. Let's decompose 2, 1, 0 with respect to the orthonormal basis E1 hat, E2 hat, E3 hat, which we can recall was 1/2, 1 plus I, 1 minus I, 0, 1/2, 1 minus I, 1 plus I, 0, and 0, 0, 1. We should recall from the previous video, possibly the most important statement of the semester, that so long as a set of vectors is an orthonormal basis, you can always write another vector, let's say for capital V, you can always write another vector as the sum over the basis entries, and you can compute the coefficients using inner products. These coefficients will then turn around and give you the vector representation E1, E2, and so on, En, if you have your basis entries that you're representing against. So all we need to do is compute a lot of inner products of our vector against the vectors in our orthonormal basis. Hence, we compute V against E hat 1, which happens to be the inner product 2, 1, 0 against 1/2, 1 plus I, 1 minus I, and 0. And if I read across horizontally, I just need to recall that I'm taking a conjugate on the right-hand side. That's going to give me a 1/2 times 2, 1 minus I because of the conjugate, plus 1 times 1 plus I because of the conjugate, plus 0. If I expand all the terms out, I have 1/2 times 2 minus 2I plus 1 plus I, or in other words, I have 1/2 times 3 minus I. Or I could write this as 3/2 minus 1/2 I. My second entry will be V against E hat 2, which is the inner product of 2, 1, 0 against 1/2, 1 minus I, 1 plus I, and 0. and I'll read horizontally across again. And remember my complex conjugate. This is going to give me 1/2 times 2 times 1 plus I, because of the complex conjugate, plus 1 times 1 minus I, because of the complex conjugate, plus 0, or in other words, 1/2 times 2 plus 2I plus 1 minus I, and this will be 1/2 times 3 plus I, or 3/2 plus 1/2 I. My final coefficient will arise from the inner product of V with E hat 3. That's going to be the inner product of 2, 1, 0 against 0, 0, 1. And I can already tell my life is going to get quite easy, because reading across horizontally, I have 3 copies of 0. Therefore, what I've constructed is my first coefficient, my second coefficient, and my third coefficient in my vector representation. So my vector representation will be 3/2 minus 1/2 I, 3/2 plus 1/2 I, and 0. With respect to the basis, E hat 1, E hat 2, E hat 3. I could also write this as the decomposition, 3/2 minus 1/2 I, E hat 1, plus 3/2 plus 1/2 I, E hat 2. I could write plus 0 E hat 3, but I can also omit it if I want to. This is the vector representation and basis decomposition. Anyway, that's a really good collection of practice. You can see we're getting all sorts of practice with complex algebra, as well as inner products and orthogonality. See you in the next video. Bye.